All right, welcome back to Rock the JVM's Scala at Lightspeed. I'm Daniel, and in this video, we're going to talk about Scala as an object-oriented language. Now, this video assumes that you've watched the previous parts of the series. So if you haven't, go ahead and watch them first and then come back to this video. So we are back to our project where we write some practice Scala code, and under the package com.rockthejvm, I'm going to create an application specifically for this video. So I'm going to create a new Scala class, and like the previous video, I'm going to create a class. I'm going to name this object orientation, and I'm going to make it an object, and I'm going to make it extends app so that we can actually run our code if we wish. Now, in this video, I'm also going to explain what object is and what extends app means. All right, so Scala is an object-oriented language. Now, being an object-oriented language means that Scala has these concepts that you've probably seen in other programming language. For example, we have the notion of a class. So if I define a class called animal, then I can use this type throughout the rest of my code. And I can instantiate this class, that is, I can create a concrete representation of this type in memory by the constructor new. So I can say val unAnimal as new animal. And here is how I've created an instance of this class. So we have the notion of class and instance. Right? And instantiating is obtained with the keyword new, much like C++ or Java or other programming languages. We also have the notion of inheritance. So for example, I create a class called dog, which extends animal. And extending an animal means inheriting all its members and all its methods. So inside a class, you can define fields in the form of vals. So val, let's call this age as an int. And let's say it starts as an age of 0, and def, let's call this eat as print line, I'm eating. Right? So if you define a class, you can define members and methods. And inheriting from a class or extending a class means inheriting from all the methods that the superclass, in this case animal, contains. So the class dog will also have an age and the eat method. Now, if you don't have anything to add, you can leave this code block blank. That is, you just inherit from the animal type. Another thing that I want to show you is how to pass arguments to a class. So a dog, let's say it's a pet and it has a name as a string. This is called a constructor argument. That is because a class definition, that is class dog with the argument name, is also the constructor definition. What do I mean by that? If I want to create a dog, I will create a new dog with the name, let's say, Lassie. So the class definition with arguments will also specify the constructor that you will then use to instantiate an object. Now bear in mind that this constructor argument is not the same as a field. So constructor arguments are not fields. So if I try to say a dog.name, the compiler will complain because name is not available. It cannot resolve the symbol name. That is because after you construct a dog with its constructor argument, the name argument is ephemeral. It's not visible outside the class definition, and that's why the compiler is confused. Now, in order to promote a constructor argument to a field, you put in a val before the constructor field definition. And this will save the constructor argument as a member of the class. So you need to put a val before the constructor argument. All right, next thing. In Scala, we have the so-called subtype polymorphism that you see in other statically typed object-oriented languages. What do I mean by that? You can define a value called, let's call this a declared animal of type animal. So with a colon type that I have defined specifically. And on the right-hand side, I can create a new dog with the name Hachi. Now I'm declaring an animal on the left-hand side, but on the right-hand side I have a dog. So when I use a method from the animal type, for example, eat, so I use a declared animal.eat, this will actually be called from the dog class. If the dog class chooses to override the eat method, that will be called at runtime. So the most derived method will be called at runtime. All right, so at compile time, the compiler only knows that you're calling the eat method from an animal object, but at runtime, the eat method will be called from the most derived class. Now, as a very off topic, the film Hachi, or Hachiko with Richard Gere, is particularly emotional if you have some time to watch that. All right, moving on. We also have the notion of an abstract class, which means that not necessarily all fields or methods need to have implementations. So if, for example, I'm defining an abstract class, let's call this walking animal, I can create some values. Let's call this val has legs equals true, but I can define some methods, for example, walk, which returns unit, but doesn't necessarily provide an implementation. So I don't need to put an equals and then provide some implementation here. I can just leave the method signature as is, and whichever class ends up extending walking animal will need to override or provide an implementation of this method. Now, speaking of fields and methods, I will also mention that all fields and methods are by default public. So there is no public access modifier in Scala like you would do in Java or C++, but all the fields and methods are public by default. You can also restrict that by using private or protected. Private means that only the class has access to this member or method. Protected means that this class and all its descendants have access to this method, but not outside of the class. All right, so you can restrict that by adding protected or private. Cool. We also have the notion of an interface. So the interface is the term that you would use in Java to denote the ultimate abstract type, meaning you can leave everything unimplemented. So I can define a trait, let's call this carnivore, and I can define a method called eat, which takes an animal as an argument, which returns, say, unit. All right, so you can leave everything unimplemented, although Scala is very quirky in that you can also provide implementations in traits, but usually we use traits to denote characteristics of objects that we can then later use and implement in our concrete classes. Speaking of which, Scala offers single class inheritance and multi-trait inheritance. What do I mean by that? If I define a class called crocodile, I can extend a single class, for example, animal, but I can mix in multiple traits. So I can say with carnivore, and then I can add some more traits. So I can say with some other trait, if I choose to define it. And we can mix in as many traits as we like, but we can extend a single animal. And because we are extending animal and we're mixing in this trait which has this abstract method which doesn't have an implementation, we are forced by the compiler that we either must declare this class abstract or implement this unimplemented method eat. So I can define a method eat, which takes another animal as an argument, and I can implement that as I like. For example, I'm printing I am eating you, animal, or something like that. Okay, and now the compiler doesn't complain anymore. So Scala has single class inheritance and multi-trait. We call that mixing. So when we add a trait, we call that mix-in. And when we implement a method that's also present in a supertype, we call that an override, which is why we add this override keyword to implement the method from carnivore. We can also override a concrete method from animal. So we can say def eat, and the IDE is smart enough to suggest to override the existing eat method. So we can add the override keyword to provide another implementation for the eat method in the class animal if we like. All right, now let me tell you a little bit about Scala method notations and method naming, which is one of the chapters in which Scala shines in comparison with other programming languages. So if I define a crocodile, let me define a crocodile, let's call this a croc, as a new crocodile, I can say a croc.eat, and I can pass in a dog. Poor lassie's eaten by a crocodile. Or I can say a croc space eat space a dog. So methods that have a single argument can be used in this what is called infix notation, which is of the form object method argument. So this is the structure of the infix notation of a method. So this is exactly the same as above. A croc space eat space a dog is exactly equivalent to a croc.eat with the argument a dog. This is only available for methods with one argument. So notice how Scala is very expressive and very similar to natural language by providing this infix notation for methods. Let me also talk to you about method naming. So if I define a small trait, let's call this philosopher. I can define a method that looks something like question mark, exclamation mark, and I can pass in something like a thought, which is a string, and this can return unit. Now this name, question mark, exclamation mark, is a method name. Much like eat, much like walk, much like anything else, question mark, exclamation mark is a valid method name. So Scala is very, very permissive in what concerns method naming. You can define methods that can look as quirky as you like. We often use the question mark operator or method in Akka, and also the exclamation mark when we want to communicate with actors asynchronously. So this is actually used in practice. Now, if we want, we can mix in this philosopher trait in the crocodile. So we can mix in philosopher, and now we would be forced to define that method. So question mark, exclamation mark with a thought as a string. This returns unit, and we can print line, I was thinking, and we can pass in that thought. And notice I'm using an s-interpolated string, which we talked about earlier in the previous video. So we can use the override keyword again. Now, because this method, the question mark, exclamation mark, also takes a single argument, we can use that in infix notation. So we can say a croc, exclamation mark or question mark, exclamation mark, what if we could fly? So such a method would look like an operator because it doesn't look like anything that resembles a method. And I'm going to tell you something. Operators in Scala are actually methods. So if I define a val called, let's say, basic math as 1 plus 2, the plus here, which is an operator that you would expect for math for numbers, that's actually a method belonging to the int type. So if I say another basic math as 1 dot plus with the argument 2, that's actually equivalent. So all the operators that we normally use day to day, they're actually methods. All right, so this is pretty cool. We also have the notion of anonymous classes. If you've worked with other statically typed programming languages like C++ or Java, you probably know that abstract types, such as an abstract class or a quote-unquote interface, cannot be instantiated by themselves. They need to be extended by a concrete class. Now, we can have a concrete type that extends, for example, carnivore, let's call this dinosaur, as a new carnivore, and we can provide an implementation on the spot. So I open and close some curly braces, and I need to implement the def eat method, which takes an animal as an argument and returns unit. And I can return a print line. Let's call this I am a dinosaur, so I can eat pretty much anything. All right. So when I'm writing something like this, what I'm telling is, well, I'm telling to the compiler is, hey, compiler, create me a new class. Let's call this carnivore underscore anonymous underscore some fancy code, which is pretty much something that the compiler actually does, which extends carnivore. And then we can provide that implementation, which I'm going to copy. And then, hey, compiler, can you instantiate this class for me? So val dinosaur equals new this thing. All right, so this is essentially what I'm telling to the compiler when I'm instantiating an anonymous class. You've probably seen this in Java in particular. So this is what you tell to the compiler. All right, cool. So this is what the anonymous classes were about. Scala has this very interesting concept of a singleton object, which is particular to Scala. So I can define an object called my singleton. And when I define an object my singleton, I've defined the type my singleton and also the single instance of this type. So my singleton is the only instance of the my singleton type. Obviously, being a type, you can also add values and methods. So you can, let me put the comment over here, you can have a val, let's call this my special value, as, I don't know, you can put in any number you like, and define my special method, which can take any arguments you like, can return any type you like, and I can return another number, for example. And you can use my singleton just as that. So you can say my singleton dot my special method, as you would on any other value. Now let me show you something else. We have a special method in Scala that we call apply, which can take any arguments, and this can be present in any class, in any object, wherever you like. So if I define a method called apply and I pass in some arguments, let's say x as an int, and I return x plus 1, the presence of an apply method in a class allows instances of that class to call the applied method in the following way. I can call my singleton.apply with the number, I don't know, 65, or I can simply call my singleton with the number 65. So this is equivalent. So when you say my singleton and you open and close parentheses and you pass in arguments, the compiler automatically interprets that as a call to the apply method. This particular trick is very useful and will prove very useful in the next video where I'm going to talk about functional programming. So the presence of an apply method in a class allows instances of that class to be invoked like functions. So notice that I'm basically invoking my singleton with the argument 65. This will be very useful when we talk about functional programming. Now back to singletons. In the same file, that is in the same place, you can define a class that is, for example, animal that we defined above, and a singleton object in the same file. So if I define an object called animal, that is perfectly acceptable to the compiler. In this particular case, the class animal and the object animal are called companions. And this is called a companion object. That is because it has the same name as an existing class or a trait. This can also be applied to traits. Now, companions have the additional property that they can access each other's private fields or methods. However, the animal singleton object and instances of the animal type are different things. So the singleton animal and instances of animal are different things. This can be really hard to wrap your head around, but you normally never use the animal as an instance while other animals are present in practice. You would normally use the animal companion object to access things that do not depend on instances of the animal class. Let me give you an example. Let me define a small value in the singleton object animal. Let's call this can live indefinitely as false, because at the moment of this recording, there is no animal that can live forever. And you can access this field as, let's call this animals can live forever, as animal dot can live indefinitely. So you access this field on the singleton object in much the same way as in Java or C++ you would access static fields or methods. So that was with objects and companions. Let me talk about case classes. And case classes are a very common pattern in Scala because they are lightweight data structures with some boilerplate. So when I define a case class, so notice I'm using the case keyword before the class definition. Let me define a case class person with a name as a string and age as an int, for example. Okay, when I define a case class person, the compiler automatically generates the following for me: a sensible equals and hash code for inclusion into various collections that rely on equality and hash code. Sensible and quick serialization, because we often send these instances over the wire in distributed application, in particular with Akka, for example. We also have a companion with apply. That is, I can define, let's call this val Bob, as new person with the name Bob and age, let's say 54, but I can omit the new keyword. That is because the person case class also has a companion object with an apply method that taking a name and an age and spitting out a person instance. So case classes may be constructed without the keyword new. And various other things, including pattern matching, which I'm going to talk about in this series. So this is actually equivalent to person.apply with the string Bob and the number 54. That is because the person companion object is automatically generated by the compiler when you write a case class. Let me also add pattern matching here, because we're going to refer back to it when we discuss pattern matching later in the course. Now, let me talk about exceptions. Scala, as you know, is based on the Java virtual machine. So all the Scala code that we write is actually compiled to Java virtual machine bytecode that can be then run on every single device that has a JVM installed, like an Android phone or a computer or anything else that can run Java can also run Scala. The JVM also has this notion of exceptions, which means that if one of these objects is thrown, this is the correct term, then the JVM will interrupt its normal code flow execution. And exceptions are special objects treated by the JVM with these try catch expressions. So I can write some code that can throw. So for example, I can say val x as a string, and I can call a method that returns null. You're probably familiar with the null reference. And then I can access x.length or something like that. I can access a method on a field on a null object. This will normally crash the program, but in a try-catch expression, I can catch all the exceptions that might be thrown by this code with the directive that looks something like this: case e colon exception, and then an arrow, and then I can return something else, some faulty error message. So this is roughly what you would see in Java or C++ when you try and catch an exception. Although, mind you, trying and catching an exception in C++ is like trying to shoot yourself with a chicken wing or something like that. So this is very similar in structure, and this is identical to what you would see in Java, except this catch statement looks a little bit differently. It has slightly different structure. In Java, you would say catch and then exception E, and then you would open some code block to do something else. All right, so this is the structure that we use in Scala, and we also have a finally clause, which would execute some code no matter what. So regardless of whether this code that was tried and threw an exception or not, this finally code is executed no matter what. And this is useful for closing connections or closing files or releasing some resources that would otherwise be dangerous to leave open. All right, so that was a quick crash course on exceptions. And finally, in this video, I want to talk about generics. Generics are used in Java for a whole lot of reasons. It's pretty similar to templating in C++, although I know you C++ purists will jump at my throat, so I will refrain from comparing this too much to C++. But you can define, for example, a abstract class. This also works for classes, works for traits, and you can define, let's call this my list, and you can pass a type argument here with square brackets, and inside we can pass in a type argument that we normally use as single letters. So this myList class is applicable for any type that we denoted as t. And inside this class, we can have definitions or values that depend on this type t. So for example, I defined a method called head, which returns an element of type t, and a tail, which returns a myList of t. So you can use this t as method definitions or value definitions inside this class, so that when you use it later, the t becomes concrete. Let me give you an example. Let's consider the actual list implementation in Scala. So I'm going to create a val called a list, which is of type list of int. So inside square brackets, I'm passing a actual concrete type, which is int in this case. And I can construct that as list, for example, with 1, 2, 3. List applied to 1, 2, 3 is actually the list companion object applied to the arguments 1, 2, 3. You learned about the apply method earlier in this video. Now, this list object is a list applicable to type int, so that when you have, let's call this first, as a list.head, the head method returns an element of type t, which becomes concrete for this particular list to be int. And so the compiler knows that this value is of type int, because its list, on which the head method was applied, is a list of type int. And call this rest as a list.tail, which is a list of int. All right, so I've defined a myList generically typed with the type argument t, in much the same way as the Scala standard library list collection is generic. And in this particular example, I've made the type list int concrete. Now, a fair bit of wording. If you've never worked with a statically typed language before, like Java or C++, understanding generics might be a little tough. So if your whole programming experience is in Python or in JavaScript, this generic types thing might be a little difficult, all right? So I understand if this thing is a little bit tough. Now, this is just an example with a list of int, but the same list functionality can be applied to other types as well. So if I can have a string list as list with the strings hello and then Scala, this will be a list of string. So the whole purpose of generics is to reuse the same functionality and to apply it to multiple types, such as the code for collections. The code for collections should be applicable to any type that you store inside. Now, again, you C++ purists, I know you can specialize your templates and all that kind of stuff, but we are simply reusing our code here in Scala. Okay? So if I define a val called first string as a string list.head, this is a string, and the first head was an int. Right? So we're calling the head method the same head method, the same logic on first a list of int and then a list of string. And we are obtaining an int and a string respectively. Good. So that was a crash course on generics. Now, I will end this video with two very important points. Point number one. In Scala, we operate with immutable values. What do I mean by that? Any modification to an instance of a class will normally result, or should result for best practice, should result in another instance. So if I call another value, let's call this reversed list, as a list.reverse, which is a method on the list type, if you operate on a list and you call the reverse method on it, this returns a new list. Any modification to an object should return another object. So you don't mutate or change the values inside a given object, you always return another one. This is twofold beneficial. So benefit number one, works miracles in multi-threaded environment. So in multi-threaded or distributed code bases, immutable values work miracles and speed up the development tremendously. Benefit number two is that helps making sense of the code. What we call reasoning about. So when you're reading blog posts or books or watch people talk about how this framework or this tool or this mental model helps us reason about the code easier, this is what we mean. It helps us make sense of the code much easier, especially in large code bases. So working with immutable values and objects in Scala works miracles for Scala programmers. This characteristic will only become apparent with more Scala experience. So this was point number one. Point number two is that Scala is closest to the object-oriented ideal. So Scala is marketed as a mix between object orientation and functional programming. Scala is actually a very good object-oriented language. Why is that? Because all the code and all the values that we operate with are inside an instance of some type. So if you notice, every single piece of code that we have written so far is part of a class or part of an object. So given the fact that there are no values or methods that are outside a class or an object, we can call Scala a true object-oriented language. Now, finally, I will deliver a small promise that I gave at the beginning of this series when we defined our first application. So when you define an object which extends app, you're actually inheriting from the app type's main method. So you already have a main method already implemented in this object. Now, because I mentioned earlier that methods on objects are similar to Java static methods, you already have a static, quote-unquote static, main method already implemented by extending app. So it's as if you already had a Java public static void main with string args. So this is the equivalent. And this main method would simply execute this object's body. So this is why applications are actually runnable. If I cut the extends app, notice that IntelliJ doesn't actually allow me to run this application. But if I put it back, I suddenly have this object to run object orientation as a dedicated application. All right, so this was Scala as an object-oriented language. In the next video, I'm going to talk about functional programming in Scala. If you liked this video and found it useful, go ahead and click the like button and subscribe to the Rock the JVM channel, and I'll be posting more free goodies here. This video series is also available as a free online course at rockthejvm.com, where you will also have the option to download these videos for your offline use. And on the Rock the JVM site, we also have hundreds of hours of premium content dedicated to Scala, functional programming, Akka, Apache Spark, and so much more. So go ahead and check out rockthejvm.com, and I'll be waiting for you in the next video.